Oops. Okay. So let's get started a little bit before we jump into the actual topic. A few words about ScyllaDB. So ScyllaDB is the company behind Scylla, a real-time NoSQL database, which is a drop-in replacement for Cassandra with superior performance and low latency, in particular low tail latency. And by drop-in replacement, I'm mostly referring to the compatible on-the-wire binary protocol. This means that every driver that works with Apache Cassandra will work out of the box with Scylla as well. And this is important in general, but specifically for the session today, we'll talk about CDC and we'll explain what is CDC later. The feature is basically enabled with a standard CQL driver. So you can consume the update through the standard driver that you have. Scylla comes in 3 flavors or 3 variants. One of them is an open source project. You can go to the GitHub page, you can download the code, you can compile it if you are into this kind of things, you can send patches and such. We also have an enterprise variant, which is a closed source project based on the open source with some extra features, mostly around security and cluster management. And last but not least, we have database as a service, Scylla Cloud, which is basically a managed Scylla enterprise on the cloud, so you don't have to deal with installation, maintenance, repair, backups, and all of that. We are doing everything for you. The company is a little bit more than 100 people right now, and we are very distributed across the globe. The presenters. So that's me. I'm Zach, VP of Product. And by the way, the picture here is a heavily Photoshop. Piotr, I will let you introduce yourself.
Hello, my name is Piotr. I'm leading the team which develops change data capture for Scylla.
Okay, thank you, Piotr. Piotr will do most of this session. I will, in the next 5 minutes or so, I will introduce the use case for change data capture and why you should care about it. Later, the main part of this session will be a deep dive into the feature, how to use it, how it's implemented. And at the end, we'll go back, I will take control again and explain a little bit about the roadmap, a little bit comparing Scylla feature to other databases. And at the end, as mentioned, we will do some Q&A and you can start asking questions now. So what is change data capture or CDC? It's a protocol or a feature that many different databases share, each of them in slightly different way. Basically allow you to capture changes. And by changes, I mean any mutation to the database. Write, update, delete, etc., including range delete, batch writes, and all the features that Scylla provide. You can consume this update through CQL API in a completely asynchronous way. So you can develop your application, use an agent or a driver to consume it at your own pace. Of course, you need to be fast enough to catch up with all the updates, and we'll touch on that later. You can define CDC in table level granularity, meaning that you don't have to track all the table. You specify which table you want to consume the updates. The data is a standard Scylla table, and by that I mean it's highly available, it's persistent, and it's consistent the same way that every Scylla table is. So what can be a use case for capturing this kind of update? So in many organizations, you have more than one database or data source, and you might have a microservices architecture, and you want to feed in real time all of the updates from the database to other services. So for example, you can read the CDC stream from Kafka or other data queue and feed it to other databases such as Elastic, Data Lake, or whatever database that you want to use. You can run real-time analytic on this data. For example, try to identify fraud in real time and set trigger on that. And you can do analytics with tools like Spark and actually feed some of the information or the result back to Scylla. So an example of that might be what is the last 10 highest measurement of some sensor or something like that across all partitions or across a region or something like that. And you can do that with Kafka, and if you want to, you can feed the result back as a Scylla table. A subset of this feature can be that the other database that you are feeding information to is actually another cluster of Scylla. So a natural question might be, why do you need that? Scylla already have a very strong cross-region replication, which is very flexible. You can set different replication factor, you can set different consistency level between the region, and you already have that. So why would you need to use something like CDC to push information from one cluster to the other? And the answer is power versus guarantees. So with the multi-data set deployment, the granularity of duplicating information between two data centers is in the key space level, while in the CDC, as I mentioned, it can be in a table level. The consistency between two regions in the same cluster is strong or eventual. And when you're using CDC, you basically don't have the same guarantee because you don't have repair between the cluster. So it's a weaker kind of consistency between the two clusters, but it also gives you more flexibility. So for example, you can read the information from one table in the cluster, do some manipulation in it, and push it to another cluster, which might be in a different version, for example, of Scylla. So you can implement something like an active-passive replication. You can, for example, have in one cluster a TTL of 1 day, in another cluster a TTL of 1 month, etc. So it's basically give you more flexibility, but you don't have the same eventual consistency guarantee that you have on the same cluster. So with that, I would like to share a pool. I hope you can see it. So my question to you is what seems to be the most relevant use case for CDC for you guys? Either you are using this use case right now with other database, or you plan to use or want to use with Scylla. So we'll keep it up for a few seconds. And you can answer it, and we'll review the result at the end of the session. And with that, I'm switching back to Piotr, or actually switching for the first time to Piotr to deep dive into the CDC.
So next section will be based on examples. So let's look at the schema of the table that will be used for that. I think we need to turn this off. Here we go. So the table is just a simple table which has employees of some company. The employees are grouped in departments and identified by last name and first name. They also have some characteristics like age and level, so that we can have an example of non-primary key columns as well. On the right, you can see an example table with some actual data inside. CDC actually works in few different modes. It can store just the delta, the change that is happening to the data, or it can store also the pre-image, the state of data before the change, or post-image, which is the state of data after the change. Let's look at some examples of each of them. So when we talk about the delta, when we have an empty table and we insert a new employee to the table, there's going to be a new row in this table. In this case, delta is the whole new row because nothing was there before. if we insert another employee, this time it's missing the level column, we will get another row, and the delta will be this new row, but without the missing column. So no level included. If we update a row, for example, we give a promotion to John, the data in the appropriate row will change, and delta is actually a primary key plus the set of columns that has actually changed. We can also delete something, for example, an age from John's row. It's gonna get a tombstone in the table, and the delta itself will be a primary key plus a tombstone in the right column. We can also delete the whole row like this, and then the delta is just a primary key of the deleted row. Now let's see how preimage looks like. So again, an empty table. We are adding a new row, and now preimage is just an empty row because that's what was there before the operation. And just to compare it with the delta, which was the whole new row. When we update something the same way we did before, preimage is the state of the changed data before the operation was performed. Notice that age column is not part of the preimage because it wasn't part of the operation. Just to compare it with the delta so that you can compare the two. If we delete just the age, then it's going to be a tombstone again, and the preimage is the data that was actually removed, plus the primary key because we need to be able to identify the row. Again, comparing with the delta itself. If we delete the whole row, then preimage is the whole deleted row, and the delta is just a tombstone on the primary key. With the post image, let's see what happens when we update. When we update, the post image is actually the new state of the whole row. And we can compare this to delta. Notice how this is different from the pre-image because the post image contains all the columns, no matter whether they participated in the operation or not. That's why we have age in the post image. Again, we can delete the age, and then post image will look like this with the tombstone in the age column, comparing to the delta itself. And then we can remove the whole row, and in that case, we've got just the tombstone for the row. So let's have a quick look at the way CDC stores those informations. So whenever change data capture is enabled for a table, a new internal table is created for that table. So in this case, if we enable CDC for employees table, in the same key space, we will get an employees Scylla CDC Log table. The name is composed by the base table name with the suffix of Scylla CDC Log. And then let's decompose its structure. First of all, it contains all the columns from the base table, from the observed table, with the same names, with the same types. Then the columns that are not part of the primary key have an accompanying columns which allow us to mark whether this column was deleted or not. We've got also CDC TTL, which is used to track any TTL attached to the operation. And we've got a couple of columns that form a primary key. First of them is stream ID, which is a partition key. It's a specially selected partition key which controls the distribution of the log entries in such a way that they are collocated with the actual observed data, but I will talk more about it in the later slide. Then we've got CDC time, which is the time at which the operation was performed. It's not stored as a pure time, but as a time UUID to avoid clashes with other operations that were performed in the same exact time. Finally, there's a CDC operation which allows us to say what kind of operation caused the entry in the CDC log. So at the moment, we've got 9 of them. Preimage and postimage are special types to store those 2 special modes, and the other 7 are used for delta. Let's go through all of them and see what could happen, cause them to appear in the CDC log. So update is a usual update, which we can do like this. Also, deletes are updates if they are deletes of a set of columns. Insert is just a simple insert like this. Row delete, it's just the whole row delete based on the primary key. We can also delete the whole partition if we define only the partition key in the where clause. And then there's a set of range delete bounds. Those can be created if we do delete with some range in the where clause. They can be exclusive or inclusive, so that we've got 4 different types for begin and end of the range. So as you can see, all the special columns in CDC log have names starting with the CDC $sign prefix. Now, if someone wants to use CDC at the moment, it's an experimental feature. So you need to restart your node, your server, with either Scylla YAML edited and the experimental feature CDC added to that configuration file, or with a special command line flag -- experimental. Once this is done, you can create a table with CDC, or you can alter existing table to add CDC capability to that table. The CDC options here is actually a set of different options. You can enable or disable the whole thing. You can say whether you want pre-image or not, and whether you want post-image or not. And you can define the default TTL of records in CDC. By default, it's 24 hours, but you can set it to any value. In this particular example, it's 1000 seconds. So let's look how exactly the CDC log entries look like. When we do an insert to an empty table, it's gonna create a single row in the CDC log. There's gonna be some CDC stream. It's gonna have some time UUID which reflects the time of the operation. Then there's gonna be a batch sequence number, which in this case is 0. I will explain how it works later in the following examples. The operation is 2 because it's an insert. There was no TTL, so it's null. All the data columns are filled with the values, and nothing was deleted, so the CDC deleted columns are null. If we update something, then the type of the operation has changed to 1, and the data columns itself has reflected the actual change. Then we can also remove one of the columns, so delete H, for example. And here we see that the operation is 1, which means it's still an update, but CDC deleted H is set to true. This means the whole value of the column was removed. We can also remove the whole row. In that case, the operation type is free, and we've got just the primary key data columns set up. We can also remove the whole partition. In that case, the operation type is 4, and only the department column is set, as this is the only partition key column. And now we've got this range deletion. And it's a good example to show you why batch sequence number is here. This is a single operation, but it will create 2 new rows in CDC log. One will mark the beginning of the removed range, and the other one will mark the end of the removed range. So you can see here that we've got 2 rows added. Both share the same stream ID and time, but one of them has batch sequence number 0 and the other sequence number 1. You can see that they've got different CDC operations. One is 5, which is range delete inclusive open start, and the other one is 8, which is range delete exclusive end. And the only data values that are set are actually the primary key, the subset of primary key columns that's defined in this range. So with that, let's have a brief look at what's happening when a write to a base table arrives. All the CDC operations are synchronous. So when a coordinator in the cluster gets a write to a base table, it's gonna, and let's assume for a second that in this particular example, we use replication factor of 3, and the operation is done in a consistency level quorum, which in this particular example means 2 replicas have to acknowledge the write. So when the write arrives, the coordinator sets 3 writes to base table and 3 writes to CDC replicas. Then it's gonna wait for at least 2 acknowledgements from the base table and at least 2 acknowledgements from CDC. At that moment, it's gonna acknowledge back to the client, and then some further acknowledgements may come, but they don't matter anymore. So CDC Streams. You remember this CDC Stream ID, which was a partition key of the CDC log? It's specially selected. When we have a cluster on which Scylla is running, data is not only partitioned across the nodes in the cluster, but it's also partitioned across CPUs on each node. We call them shards. So the CDC stream ID is selected in such a way that data that's stored in this stream reflects data in base table that lives in exactly the same node and the same shard. Thanks to that, we can achieve high performance and quite good results. We actually got some initial benchmarks done on AWS X for large, E3 X for large machines. And as you can see in the table, Without the CDC, the throughput was around 78,000 operations per second. When just Delta was enabled, it was around 60,000, which was 20% worse. And with Delta and Preimage, it was 33,000, which was 57% worse. On the same time, mean latency has grown from 1.3 to 1.6 milliseconds. That's 23%. And in the most difficult case, when we fetch more data, to 3 milliseconds. You can also see 99th percentile, which increased from 3.6 milliseconds to 4.7 milliseconds and to 9.3 milliseconds in the more demanding case. This is sort of expected because with CDC we're doing twice more writes or more in case of Preimage. And for Preimage we also have to do a select to do read before write to obtain the actual state of data before the change. And with that, let's move back to Zach.
Okay, thank you. Piotr, can you move to, okay, thanks. I'm not sure I'm controlling the slides or not. So what are the takeaways from this session? So first of all, we did this session in an attempt to get feedback. As Piotr mentioned, the feature is not considered production ready yet, but it is available as experimental in the latest version of Scylla 3.3. And even better if you use the latest Scylla build. I will show later how to do that. And we'll be happy to get your feedback on it. So to wrap up the advantages or the use case for CDC, it's easy to integrate and consume because it's used standard driver and a standard CQL table, which you already know how to work with. It's robust, it's replicated. So even if a node is going up or going down or network restarts or anything like that, the data is replicated the same way every other table in Scylla is replicated. So you get the same level of high availability. It's have reasonable overhead, as Piotr mentioned. Of course, it has some overhead because you need to write the mutation and you need the extra write and extra read, so it have an effect. And last, you cannot kill or slow down the database if you are not consuming data fast enough. The data in the CDC table is a TTL, meaning its time to live is limited. The parameter is configurable and you can set it higher or lower, but at the end of the day, usually the data will be deleted, even if you are not consuming it. And that's keeping us from overloading as a storage. So a little bit about how this feature similar or different from other CDC or stream feature in other databases. So you might notice that the features of Scylla are very similar to DynamoDB streams. Like DynamoDB, Scylla produces a pre-image and a post-image of every mutation. Unlike Dynamo, it also provides the actual delta between the pre-image and the post-image, so you can choose to consume either one of these three elements. The implementation of Scylla is very different from the implementation of what is called CDC in Apache Cassandra. In Apache Cassandra, at least the latest I've seen, the CDC feature is based on commit log in each of the node. And that means you cannot use standard CQL a driver to consume it. You have to do a deduplication yourself. The data is not TTL. So although the name is the same, it's not compatible in that sense. Usually we try to keep compatibility with Cassandra, but in this specific case, we felt that the Cassandra implementation is not mature enough, so we choose another way. As mentioned, you can try Scylla CDC right now. The easiest way to consume it is go to a Docker Hub. There is a Scylla nightly Docker image that you can download and run. Keep in mind that you need to run the experimental flag to enable that. And once you do, you can actually use CDC. Everything that Piotr has mentioned and more even is in the documents. So you have the link here and we'll share it after. You are more than welcome to go over the documentation, run the feature and share your feedback. And with that, let me, just before we jump into the Q&A, let me go back to the pull results. Okay, I assume you can see the result, but if not, I will read them out. So the most popular use case that people are thinking about is pushing in real-time data from Scylla to some other database like a data lake or a data warehouse. And the second after is soft real-time analytics, which might be with Spark or other analytic tool, Presto or what's not. Every tool that can consume stream and act on it will be a good fit here. So with that, let me jump to the Q&A. And Piotr, I will read a few questions to you, and if you can, I would answer the easiest one and push the more complex question to you. So the first question, are CDC supported with Alternator? So those of you who are not familiar with Alternator, Alternator is a Dynamo API compatible API with Scylla, which is also an experimental phase, but will be GA very soon. So the answer is not yet. CDC will probably work with Alternator, or maybe even now to some extent, but it's not compatible with DynamoDB Stream yet. We're looking into it, and we're looking for feedback from the community how useful such feature can be. So second question from Radu. What delivery guarantee of the CDC does Scylla offer? At least once, exactly once, at most once. So Piotr, do you want to get that question?
Yeah, let me take that. So I'm not sure how clear it was from the presentation, but CDC Log is just an ordinary table in Scylla. So consuming it is like Kafka. So you pull the data, and you can set it up in different ways to get different guarantees. It's up to you whether you're gonna consume it in such a way that you have at least one or at most one. Exactly one is a bit harder, but again, it's the same model as with Kafka because it's the client pulling the data. So, so it's configurable.
Okay, second question is from Sai. How do I stream CDC data to my Kafka node and from Kafka to Scylla, Elastic, etc.? So there is a short answer and a longer answer. So we are working on a reference implementation of that will open source soon, that will demo it. Right now, it's something that you have to write for yourself, meaning a client that uses standard driver to read information from the table and push it to Kafka. We do have a Kafka connector that we recently released. That I will share maybe the link to this after the session. So the quick answer is that you have to do it yourself. The longer answer is that we plan to publish a reference implementation of that. And one more question. How is it different from a redo log of Oracle? So
I can take it, I think.
Okay, thanks, Piotr.
So it is very similar. It's just for a distributed database. So that's the biggest difference, right? That now we have to give you the redo log of a distributed cluster. So it is very similar, and one of the use cases for this is the replication of the database. So in that sense, you can take operation after the operation from CDC reapply it to another database, and that would be like redoing the operations.
Okay, thanks, Piotr. I don't see more questions, and we are almost out of time. So thank you very much, everyone. And we will share the presentation and the recording soon. Have a good day, good night, and stay safe.
So I think we've got one more question, whether we have to enable CDC on every node. And this works this way. You need to enable CDC on each node to be able to enable it on a particular table. Once you enable CDC on a particular table, it's working on the whole cluster on all the nodes. It's just that you have to set the feature flag on every node to get the functionality working there. And only after you've got it on, enabled on every server, it allows you to start working with it. In the future, when CDC is not experimental anymore, you won't need to do anything with the nodes. You will just do create table with CDC or alter table with CDC, and then it's gonna be working across the cluster.
Okay, thanks, Piotr, for this last one. Good timing for pushing it in, I guess. So thank you, everyone. Have a good night, good day. Bye.